Hello guys, this is Neha. Welcome to the 7th lesson of this course. Today we will be discussing some properties of the operation of union and intersection of sets. So, the union and intersection of the sets has the following properties: idempotent law, identity laws, commutative law, associative law and distributive law. Now let's understand each of them with an example. Let's start our discussion with idempotent laws. So let's consider a set A. The idempotent laws for union and intersection are A union A is equal to A and A intersection A is equal to A. Now, so this is the same set. This is the same set. And we are applying one of the operation of set on the same thing itself. Say, for example, you have a set A with elements 1, 2 and 3 and you need to find A union A. What will be A union A? A union A will consist of these elements 1, 2 and 3, which is same as set A. So A union A is equal to A. Now let's see A intersection A is equal to A with an example. Let's consider a set A with elements 4, 5 and 6. Now what will be A intersection A? A intersection A will consist of the same elements 4, 5, 6, which is again A. So we can say that A union A is equal to A and A intersection A is again equal to A. That is, the process of applying an operation on itself is what known as idempotent law. So the next is identity laws. Here we will be using two important identities in set. One is empty set and the other is the universal set. The empty set is the identity element for the union of sets and universal set is the identity element for the intersection of sets. The empty sets is represented by phi and the universal set is represented using the letter U. Now let's see what are the identity laws of sets. A union of an empty set will give you A union of an empty set will give you the set itself and A intersection of the universal set is A itself. Let's see an example. Here A contains the elements 1, 2 and 3. Now A union empty set will be the same set itself, that is 1, 2 and 3. Now let's see another example. An example of A intersection universal set. Here A contains the elements 4, 5 and 6 and the universal set is the set of natural numbers. Now A intersection of the universal set will consist of the set A itself. Hence the identity law states A union empty set is the set A itself and A intersection universal set is again the set itself. Now let's see commutative laws. The commutative property for union and the commutative property for intersection say that the order of sets in which we do the operation does not change the result. A union B is equal to B union A and A intersection B is equal to B intersection A. Let's see this with an example. Now let's consider a set A with elements 1, 2 and 3 and a set B with elements 4, 5 and 6. Now what will be A union B? A union B will consist of the elements 1, 2, 3, 4, 5 and 6. And what will be B union A? B union A will again consist of the same elements, that is 1, 2, 3, 4, 5 and 6. So as the sets are same, hence we can say A union B is equal to B union A. Now let's check A intersection B is equal to B intersection A. Let's consider a set A with elements 4, 5, 6 and a set B with elements 4, 5, 7 and 8. Now what will be A intersection B? The common elements between the sets A and B. So what are the common elements? The common elements are 4 and 5. So A intersection B is a set with elements 4 and 5. And what is B intersection A? Again, B intersection A is a set with elements 4 and 5. So A intersection B is equal to B intersection A. Hence, we can conclude that the order of sets in which we do the operations does not change the result. Now let's see associative law. The associative property for union and the associative property for intersection says that how the sets are grouped does not change the result. Let's check this with some examples. Here, let's consider the sets A, B and C. A contains the elements 1, 2 and 3, B contains the elements 4, 5 and 6 and C contains the element 7. Now, see the left hand side. It's A union B union C, where A union B is within parenthesis. So let's perform first A union B. So A union B will contain the elements 1, 2, 3, 4, 5 and 6. And then we need to do A union B union 6. Union C, sorry. So it will be 1, 2, 3, 4, 5, 6 and this 7. Okay. Now if we perform A union B union C, that means we need to first find B union C and then we need to union it with A. So what will be B union C? B union C will contain the elements 4, 5, 6 and 7. And now A union B union C will contain again these elements 1, 2, 3, 4, 5, 6, 7. Hence, this is true. Now let's check the associative law for intersection. A intersection B intersection C is equal to A intersection B intersection C. Here, again let's consider three sets A, B, C. A containing the elements 4, 5, 6. B with the elements 4, 5, 7 and 8. And C with the element 4. Okay, so firstly we will find A intersection B. So A intersection B will be a set containing the elements 4 and 5. Now A intersection B intersection C will give you a single element, that is 4. A set containing a single element 4. Now let's check the right hand side. A intersection B intersection C. In this case, firstly you need to find B intersection C. So B intersection C will contain a single element, that is 4. Okay. And now A intersection B intersection C. As the common elements between A intersection B intersection C is 4. Hence, again A intersection B intersection C, this set contains only one element, that is 4. Hence, this is proved. Thus, the way the sets are grouped does not change the result. Now let's see the distributive property. Now we'll understand distributive laws with the help of Venn diagrams. So the first distributive property is A union B intersection C is equal to A union B intersection A union C. Okay. Now here is the left hand side and this is the right hand side. You can see three Venn diagrams. These are for the right hand sides and these two Venn diagrams, these are for the left hand side. So let's see, to start with the right hand side. So first is A union B. What will be A union B? A union B is this colored area, yellow plus red. Okay. Now what is A union C? A union C is this colored area, yellow plus red. Alright. Now let's do A union B intersection A union C. Now what are the common parts between these two Venn diagrams? We can see the yellow portion, the yellow colored area is common, isn't it? And then this red area, only this portion is common. Hence, this red portion is common. So what will be A union B intersection A union C? This yellow plus red colored area will be A union B intersection A union C. Now let's see the left hand side. So firstly we will do B intersection C. So what will be B intersection C? This is B and this is C. So B intersection C will be this part. And then we need to do A union B intersection C. We know A is this part. So we'll just color this using yellow. So we get A union B, B intersection C. So this is our left hand side. You can check A union B intersection C. And this is our right hand side. Isn't it? Now you can see the Venn diagrams for the left hand side is same as for the right hand side. Hence proved. Okay, now let's see the distributive law, the next distributive law, that is for the intersection. Again similarly, here these three Venn diagrams are for the right hand side and these three Venn diagrams are for left hand side. So let's start with A intersection B. This is A and this is B. So this portion is A intersection B. A intersection C. So this portion is A intersection C. Now what is A intersection B union A intersection C? So you can see this is the A intersection B, this is A intersection C. So this complete part will be A intersection B union A intersection C. Now let's see the left hand side. So left hand side, firstly let's draw a Venn diagram for B union C. So this is B union C, the complete red plus yellow colored area. And now we need to find A intersection B union C. You know this is A. So only this area is shared with A. So A intersection B union C will be only this yellow colored area. And the yellow colored area is same in both of these Venn diagrams. So the right hand side is equal to left hand side. Hence we can see the distributive property holds true for intersection. Okay, hope by now you are clear with the properties of operations. In our next slide, in our next lesson, we will see properties of complement of a set. Thank you.